it's my honor to chair John's talk. This is the fourth the master lecture series. The last one is the best one. So, Professor John Suppe is currently still the distinguished chair professor in NTU, also the distinguished professor in Houston, and also Princeton. John got the PhD degree from Yale, and shortly he go to the UCLA with the assistant professor. Then John moved to the professor in Princeton. Right. And 2007, John moved to the full-time distinguished chair professor in NTU until 2016. So moved to the University of Houston. John got a lot of the award. John also the member of Academy of Science of the United States. So at least I remember John got twice time the best publication award in the Geological Society of America. And John also got the Career Contribution Award from the GSA. And John proposed the critical taper wedge model is very famous for the mountain building. And the last 10 years, I guess the last 10 years, John also worked in the large scale about plate reconstruction. And basically, John to work in Taiwan pretty early, about 40 years ago, John already worked in Taiwan. He also the visiting professor in NTU. So John knows Taiwan pretty well today. I guess it's the latest result from the research in Taiwan. Now, welcome, John.
Great, thank you, Yimin. Actually, a lot of what I'm going to talk about today was inspired by coming to Taiwan and being in the same building with Yimin, and particularly all the work with tomography. At Princeton, across the hall, there were various tomographers, Gus Nolet and Tony Dolan, but I never did anything on tomography there. But it was really in Taiwan that I got started. So, yes, we have these amazing mountains in Taiwan. It's like the Alps sitting off the coast of maybe the southeastern United States or something like that. An arc-continent collision going on. And so what is underneath Taiwan is a big question. And it's been a big question in my mind for since I first came to Taiwan in 1975. So it's a long time ago, before some of you were born, I think, probably. And so there used to be this Far East Air Transport Company here. So yes, this is actually work that involves a number of people. Here are some of the people that have contributed to this. Yimin's in here. And basically, here's the island of Taiwan, the topography there, and then maybe the shoreline of mainland China, Luzon down here. And then, but this is a slice through a tomographic image. This is an acoustic image of the Earth, and the colors here are the higher or lower speeds. The reds are very slow speeds that are associated with high temperatures, and then these higher speeds here are colder things. These are subducting plates. The Philippine Sea Plate comes into northeastern Taiwan, and the Eurasian Plate goes from Taiwan south towards Luzon. And so I want to today mainly talk about different aspects of the relationship between these deep things that are seen in the mantle. In fact, even going much deeper than this. We'll be going down to maybe 2,000 kilometers today. But also, I think I should start off at the surface of the Earth, because the best information we have about the Earth is actually on at the surface. And here's the, here is this, oh, I should have mentioned in the previous slide. Let me try to go back. Sorry. I just wanted to point out that we have subduction of the Philippine Sea Plate under the Ryukyu Trench, but the subduction of the Eurasian Plate under the Philippine Sea Plate. So this has been known for a long time, and this is a diagram that has been published many, many times and discussed, but we know that the Philippine Sea Plate is subducting northwards and the Eurasian Plate westwards, but what's going on where they come together? We haven't known. This diagram doesn't explain that at all, and so we want to find that out today. And also there are various kinds of rocks here. These are volcanic rocks that have come in with the Philippine Sea Plate, part of the Luzon Arc going down to Luzon, and then various metamorphic rocks and sedimentary rocks of the China continental margin that are deformed in the mountain belt. And now this is a very well imaged area, so it's probably the best place in the world for studying the internal structure of mountain belts. In Japan and Taiwan and also in mainland China, there are tremendous numbers of seismometers and also lots of earthquakes, so those can be used to do imaging of the inside of the earth. And so this is advanced very rapidly in Taiwan, and I would say it's the best imaged mountain belt in the world at the moment. And but let's start at the surface, and then I'll take you down maybe just 5 or 10 kilometers, and then maybe 10 to 50 kilometers, and then finally down to maybe 1,000 or 2,000 kilometers in the earth, and apply all these things to Taiwan, this island of Taiwan. So Taiwan is actually converging very fast. It's the fastest converging classical mountain belt in the world. It's almost 9 centimeters a year. And the remarkable thing about this that's been very interesting to many people is it's oblique. So the continental margin of China runs northeast southwest, but the Luzon Arc, the edge of the Philippine Sea Plate, is north-south. So it collides first in the north, and then just now in the southern Taiwan, it's just starting to collide at the edge of the continent. And then maybe in the future, it'll collide with Hong Kong, something like that. And the other thing is that there's this change of polarity with the Eurasia Plate subducting under the Philippine Sea Plate to the south, and the Philippine Sea Plate subducting under Eurasia to the north, with these two plate boundaries coming in together perpendicular to one another. So how does that actually work? Many people have published papers on that. There are a lot of different ideas of how you change the polarity of a subduction system. But Taiwan is a place where you can actually figure out what the reality is. Now, for a long time, people realized that there's the South China Sea, some mid-Cenozoic ocean basin here, and presumably the edge of the continent continued all the way up to Japan. And then the Philippine Sea Plate came into this picture and collided. And given the sort of motions we have today, we'd collide maybe first over here, and then the collision would, but the plate is actually moving in this direction, northwest, towards the northwest, but it's like a wave. You can think of a wave coming up against a beach, and the beach is running northeast, southwest, and so the wave will first crash here, and then it'll crash here, and here it'll crash here. And so the mountain belt, the mountains of Taiwan, the island of Taiwan is like a wave that propagates along the continental margin. And the rock doesn't move in that direction, but the mountains, the wave moves in that direction. So it's a wave propagation problem in a sense. So, and we see evidence for that. There's actually the dead mountain belt is present north of the Okinawa Trough. It's called Taiwan Xingzi Fold Belt. And this is actually the wave that broke. It's the front of the mountain belt. It actually continues to the active part of the mountain belt down here. It changes from active to inactive in northern Taiwan. There's also part of the Taiwan mountain belt is exposed in these islands of the Ryukyus south of the Okinawa Trough. So what we have is basically a mountain belt growing out of the ocean in southern Taiwan as the plate collides. In the middle of it actually stays about the same size, and then in the north it actually dies and disappears back down into the ocean and is split apart by the Okinawa Trough. And so we get to see this whole life and death, birth, middle age, and death in this one mountain belt here. It's really a classic place in the world for something like that. And because of this obliquity, if you go southwards, you can sort of see what the situation was farther back in time at any given place. So these are things we've known for a very long time. Another aspect of this is that the mountain belt rises above sea level in Hanchuan and gets wider and wider, but then right about here it has a constant width. And so that gave the idea that it's actually eroding as fast as it's growing in central Taiwan. And so so the erosive flux is going to be equal to the compressive flux. So people have worked on that a lot in Taiwan. It's probably the most famous place in the world for something like that. And there's a lot of aspects of this that are still being explored and debated. But the idea is, sort of the simplest version of steady state is that just the amount of material that's being pushed into the mountain belt, which would be some thickness times the plate convergence, is going to be equal to the erosion rate times the width at steady state, something like that. And so and it turns out that the data for Taiwan shows that. But it also raises an issue that I want to talk about that's more the focus of this talk is, what is the thickness of a mountain belt? Mountain belts actually have thicknesses. How thick is this Taiwan mountain belt? That is, the rocks that we see in the mountain belt are highly deformed at the surface, but they're almost always just upper crustal rocks, or maybe a little bit of lower crustal rocks, but we don't see the lower part of the plate at all. And so here in Taiwan, we have a lot of evidence for this. Here was the Chichi earthquake in, I guess, 1999, and this is the surface rupture. And if you look at a geologic map of Taichung's here, and the red line is the surface rupture of that earthquake, and it's running parallel to bedding in the Jingshui Shale, this blue unit here. And then all the younger rocks above it, the Jolan Formation, Tokushan, they're all parallel to it. So they're all running parallel to the fault. And that's really telling you that the fault is a bedding parallel fault. And so you can just measure the stratigraphic thickness there, and you can figure out the thickness of the mountain belt in this region. And a little bit to the west, actually, is the Pakoshan Incline. It's a place that I've had. There's some tea that's grown there that I like very much. It's a great place for that. But you have this fault stepping up. It's actually a blind fault. It doesn't come to the surface. But this is the Chelampu fault that broke to the surface in the Chichi earthquake. And those faults come down to about 4.5, 5 kilometers deep. So that's the total thickness of the mountain belt there. It's a very thin thing, even compared with the crustal thickness. And here, just extending the cross-section, it gets a little bit deeper as you go farther back in, but it's still 5 to 7 kilometers thick until you get to the Dili thrust, and then it actually goes quite a bit deeper because it's much deeper rocks, but still not very deep. Here's a section that we made some years ago, and it comes down to about 11 kilometers. 11 kilometers is pretty common for the main part of the mountain belt. The other thing that you'll see here is that if you unfold this, you can see there's a lot of shortening in here. And so there's the deformation, the plate convergence is taken up by this deformation. But what happens below that, the bottom of the mountain belt? What's going on below the mountain belt? That's a question we need to consider. Well, we're just going to continue that cross-section, we made that cross-section before we had any tomography. So this is some tomography. I think this is from Huang Xinhua, who's Hui Min's student. And one of the things you see when you just put this cross-section on top of the tomography, you'll see that there's a velocity inversion. You go from higher velocities to lower velocities here, exactly where we expect it. These are deeper rocks that should have higher velocity. And then there's actually a deep sedimentary basin. We already knew about that because we see the upper part of the basin has been clipped off and is carried forward in the thrust belt. Okay, here's another section I want to show that goes north-south in the mountain belt. This is also tomography from Xinhua. And so this is south and that's north. And then the base of the mountain belt is this, what I'm calling the subduction interface. And you see the blue above the subduction interface. So you're putting higher velocity metamorphic rocks over actually these deep sedimentary basins. And there are actually less metamorphosed materials down there. And then finally, the base of the crust is way down here. So generally in the interior of the Central Mountains, the thickness of the mountain belt is just a little bit over 10 kilometers thick there. Okay, so what happens below? Well, it's basically, this is very typical of many mountain belts in the Earth. The plate convergence is taken up by a lot of folding and thrusting and things like that. Very big earthquakes like the Chichi earthquake. And then below, it's just subducting, and in fact it bends down and goes pretty much straight down here. Now there are earthquakes below the main subduction interface, but none of them are very big. They're not big enough to take up very much of the plate convergence. The plate convergence is taken up mainly on these very big earthquakes like the Chichi earthquake. Okay. And if we take off the mountain belt, let's see what's underneath the mountain belt. And so here's the mountain belt in this map by Andrew Lean. And we actually know out in front of the mountain belt there are various sedimentary basins that have been explored by a Chinese petroleum company. And where do those basins go? It turns out that they actually go, the bottoms of those basins go underneath the mountain belt. And so this is a map at the top of the lower crust, so it's below that 10 or 11 kilometers. A lot of these basins are quite deep. This one goes down to about 30 kilometers, I think. This one is to 35 kilometers. This is, Tainan is there. This is the edge of this is the Tainan Basin, goes completely under the mountain belt here. It gets down to about 22 kilometers there. It's a very thick sedimentary basin underneath the mountain belt. And this north-south one is an interesting one. It was the one I showed you in a cross-section earlier, but yeah, I had shown you this cross-section. There was a deep basin. And if we go and look at the seismic velocities in these deep basins, because we have both S-wave velocities, shear waves, and pressure waves, P waves. And most rocks lie along a straight line like this that relates, we have a constant ratio of Vp to Vs, or more or less constant ratio. But quartz, the mineral quartz is very different from that. And so quartz or quartzite, a quartz rock would be over here. And so we find that the rocks of these basins actually are very quartz rich. And that's actually very interesting geologically because it's the same kind of thing that you have for the Shuishan range of the Central Mountains. The Shuishan range is composed of a lot of very quartz-rich sandstones and conglomerates. And so the Shuishan range actually has those kinds of quartz-rich materials. And in fact, I didn't show you tomography under the Shuishan range, but it actually shows these characteristic velocities that are associated with quartzite. So we think that the Shuishan range is actually one of these deep rift basins that have been clipped off and carried forward. I don't have a map to show you today because I don't have too much time, but these rift basins, these are Eocene and Oligocene, Middle Cenozoic, they actually continue up into the East China Sea. There's a whole system of these that includes Taiwan. So these are the rift basins right here. And then this is the edge of the continental margin. From that tomography, but also from some other tomography, some deeper tomography that I'll show you. And so we can actually reconstruct the continental margin. And I think maybe the next, I forget the next slide, might be a section here from Tainan right off the edge of the continent. So it's a section right at the beginning of subduction of the continent. And we're going to start off with Tainan. This is Tainan anticline. And Marilyn LeBéon at Central University and I worked on some cross-sections through here. And this is where the Meinong earthquake was. It was quite damaging. And I'll tell you a little bit about that earthquake, also Jiashan earthquake. And then we're going to continue across the Central Mountains in a cross-section. But we'll start with just a seismic line from Zhongguoshi or Gongsa. And you probably can't see too well, but there's Tainan anticline is right here. It's above a fault, and it's uplifting at a centimeter a year. It's a very unusual structure. Tainan City is uplifting above this fault, and the fault comes down to about 4 kilometers, almost exactly 4 kilometers. From the seismic reflection data, you can figure out where the detachment, where the base of the mountain belt is, and it's only 4 kilometers under Tainan, and that's the front of the mountain belt. And so now we're just looking at this area here, and then we've been able to trace it down, and it steps down a little bit deeper. And this is controlled by a lot of petroleum data from Turkish Petroleum. But the Meinong earthquake was way deeper. It was about 18 kilometers. And so how does that work? Well, we'll combine it with tomography. Here's Xinhua's tomography, and it's this detachment, the base of the mountain belt steps down, and we have the same velocity inversion. We go from the metamorphic rocks into actually the Tainan Basin. The Tainan Basin comes in here, and then the Tainan Basin starts to subduct, and you can see the velocities are getting greater. Part of that may be smearing of velocities with higher velocity things to the sides, but also these rocks are going to be metamorphosed. So these are going to be slates and schists, and maybe these velocities would be garnet schists, or if that's what they are down there. But the lower crust disappears here, and so this is really the edge of the continent right in this section right here. And then if we look a little bit deeper, we go down, we have just the subduction of the Eurasian plate. This is the Benioff zone. These would be oceanic materials. There's another little subduction system of a piece of the Philippine sea plate is broken off and is subducting here as well. But the main thing is that the mountain belt itself is just this little skin here, the very thin zone that's only 5 or 10 kilometers thick. Everything else is taken up by subduction. And in fact, in the global tomography and regional tomography, we can trace this down to about 450 kilometers, and that's the total amount of subduction there's been of Eurasia. And we can actually go in and map this subducted plate. I'm going to show you a slice through this at 250 kilometers depth. And so here is the shore of mainland China. Hong Kong is here. This is the island of Taiwan, and then the Ryukyu Trench. And so here's the Philippine Sea Plate, and here's the Eurasian Plate. And then this red stuff is hot material, asthenosphere in the mantle. And so I want to show you how we might map this. We essentially have the plates, and then we have the more fluid asthenosphere. And so if we look at, there's a steep gradient in the seismic velocity around the edge of the plate. And so we can actually locate the edge of the plate from the gradients here. And we find the edge of the bottom of the Philippine, or the Eurasian plate, actually it goes way north of Taiwan. It comes way up to the coast China, Fujian there. And so those arrows show the edge of the plate going way up here. It's because of the hot material here that we know where it is. And so this is where we map out the edge of these plates. And so you can see that the seismic velocity in these plates is not very homogeneous. You have different kinds of mantle lithosphere that's been subducted there. You can also see that the two plates come together orthogonally at depth as well, just as we see at the surface, they come together orthogonally. We're not seeing any break off of any slabs or anything like that. And so this is how we would map out these plates. And I want to show you a slice through the middle of this plate here, and then actually extending up into the hot mantle. So this is what I call a mid-slab slice. And then we'll look at it first in 3D, and we'll see the outside, the outer edge of these different slabs. And so here we're looking towards the southeast. So there's the island of Taiwan, and Luzon would be down here. This is the Ryukyu Trench going up to Japan. And then the top of the plates are sliced off, I think, at about 100 kilometers. So this is the Eurasian slab coming up north of Taiwan, and then there's a northern edge of it. And we see the northern edge because all this hot material wraps around the edge of it. That really allows us to see it. And then the Philippine Sea slab comes in perpendicular. Now I'm going to show you a different view of that. This is looking from Japan towards the southeast. There's Taiwan is right here. And there's this hot material that wraps around the edge of the plate, allows you to see it. So here's the Ryukyu slab coming down, and it flattens out here. And then the blue one is the Eurasian slab, and that's the northern edge of it. It comes up to near the surface, very close to the northern tip of Taiwan. And what we're seeing there is actually tells you how this system works. So there's a northern edge to the Eurasian plate. It's not at the continent-ocean boundary. It's in the continent, about 350 kilometers north of the continental margin, and there's an edge there, and it's what's called it's actually a propagating tear. People sometimes call these step faults. So as the plates continue to converge, this tear just keeps propagating, and it's a stable system, and the Philippine Sea plate continues to subduct, but it's converging in this direction. So that's basically what's going on with the big plates under Taiwan. And there's actually a special kind of magnetism that's associated with the step fault, including Dachunshan and those volcanoes. And so here is, I've taken away the Philippine Sea plate, and there's that northern edge of the Eurasian plate. This is actually the tear, insofar as we actually have imaging of it in the tomography. That's the base of the stable Eurasian lithosphere is right about here. So, and this is the mid-slab slice. So I'm going to take away, slowly take away, make it first transparent, and you can see there's different seismic velocities within that slab there. And now we're looking straight up westward on this. So there's Taiwan. This is north and south. This is approximately where the tear is. Now this tomography is not super high resolution. You have an uncertainty that's of the order of 100 kilometers in the location of these things. But then you have a fairly homogeneous velocity here that's low velocity for relative to oceanic mammal lithosphere. This would be oceanic here. This is the subducted continental mammal lithosphere. There's also some stretched continental lithosphere. There's also a flat slab underneath here that it's coming down and sitting on. So it gets a little complicated under there. But this is the edge of the continent right here that we see in that slab, preserved in the slab. So we can unfold that slab. Here's the unfolded slab. This is the present South China Sea. And then we can see the rest of the South China Sea. And it's only about 450 kilometers here. That's the original edge of the South China Sea right there. This is the part that's continent there. There's also continent down here where you have continental material from Palawan and Mindoro being subducted there as well. And then here's the ridge, the spreading ridge, which is dead now, but there is apparently a slab window there. Okay, so and then we have a question, well, what was over here? We'll have to address this. There's some other lithosphere must have been there, and it has to do with, and it's gone because the Philippine Sea Plate has come in here. And so I want to address this question of where did the Philippine Sea Plate come from? So if we ask the question, well, where did Taiwan come from? Certainly part of it came in with the Philippine Sea Plate. And parts of it came in at other times. There's actually some very old rocks in the Cretaceous and Jurassic that came in as well that we possibly will have time today to get to. But at least most of this Philippine Sea Plate, though, is Cenozoic in age. It's new seafloor spreading. But there are a few things that are late Mesozoic, Cretaceous, and so forth. And some of these ridges here are, and also the area that's immediately adjacent to Taiwan is Cretaceous. So it's very old. And so we'd like to know where was that back in the Cretaceous? Well, that's a very tough question. It's a tough question because the Philippine Sea Plate is almost entirely surrounded by trenches. And we really know plate tectonics because of spreading ridges. So there are no spreading ridges to record the motions of this plate. And so it's a kind of a tough problem. And we know that the present motion is in this northwest-southeast direction, and it's very fast, about 9 centimeters a year. And it's actually more or less the same as the Pacific. In fact, it's really just being pushed by the Pacific, and it rotates a little bit. The subducting slabs of the Philippine Sea Plate are too small to move it at that very high speed. And so, and it turns out you can show that this is not typical of the past motion. And the main thing that we know about the motion of the Philippine Sea Plate is paleomagnetism from samples around the Philippine Sea Plate and the middle of the Philippine Sea Plate from ocean drilling. And what we get from that is that since about 40 million years, the Philippine Sea Plate has moved northwards by about 20 degrees. That's basically northward from the equator. Now you can see there's a lot of uncertainty to these data and a lot of scatter. Part of that actually turns out to do to the rotation of the plate. It turns out it's rotated a lot as well. So, so that's much more northward motion than the Pacific Plate over that same time period. So let's just go backwards in time. We have because of subduction, we have a progressive loss of information. You can see that as we go 15 million years, 20 million years, there's huge amounts of black showing up here. This is all the lost lithosphere. And so if we go back to just still the beginning of the Cenozoic, and there's a little bit of the Philippine Sea Plate. That includes the Huatong Basin just east of Taiwan. Is that better? Should I use that one? Okay. We know that it's roughly in this position at 40 million years. It's very close to the equator, but we don't. It could be any place in here. And so, and all of this is just completely lost. So we don't really know very much. That's been the problem, is there's been a huge loss of information. And so here at Taida, we develop a strategy of mapping subducted slabs in the mantle and unfolding them. And it turns out you can see a lot here. So for example, here's the Eurasian slab coming down. And then this is another slab, something we call the Proto-South China Sea and East Asian Sea. This is the Pacific slab coming down here. Here's deeper ones. This is one that we're recently been calling the Taipei slab. And there are other ones going all the way down to the core mantle boundary. And so it turns out that you can actually use this information in some quantitative way to figure out the past history. and we just have to get in and map these subducted slabs. So it's fairly complicated. So here's looking southeast from Korea. This is the Pacific plate on the left, coming down, subducting under Japan, and then it flattens out. It sits on the transition zone, and then over here is the Ryukyu slab, and it comes down and sits on top of the Pacific plate. And then there's another flat slab over here. We're just seeing a little bit of the East Asian sea slabs. And so we just need to map these things, and we developed some techniques for doing that. Here we might have a slice through the tomography, and we also have earthquakes here. Maybe we draw a line and we think, well, maybe that's the middle of some slab. And then we can do that with many, many slices, and we can develop some self-consistent mesh of these things. And then we can make a surface from that, and then we can actually put the seismic velocities and other information on that surface. And then we can unfold these things. We have some code for flexually unfolding that, minimizing distortions and changes in area. And so now it's a spherical shell, part of the present Philippine sea plate, because this is the Ryukyu slab, and it's connected right today still to the Philippine sea plate. So we can unfold it like that, and we unfold various pieces, and this is the original size of the Philippine sea plate before this subduction. And then we can use that in plate tectonics. But we can't just use this because that's just the maximum size, but it's changing. Oh, but we can already tell, actually, already this amount, this size actually rules out a lot of different plate models of the Philippine sea plate. Most of them don't satisfy the shape of this. Now, maybe the other pointer is actually better, actually, this one at any rate, so here's that Philippine sea plate, but we know the ages of different parts of that plate, and so we can actually... This one. Yeah, okay, great. Thank you. Yeah, good. So in this case, we can, where's this? Yeah, so I'm going to show you a little movie. This is the Philippine sea plate through time. And so our problem is a picture puzzle problem. So we have this piece and we want to fit it into some picture puzzle, but it has a different size and shape at each time. And so we can figure out how it changes size and shape with time. And we'll use that in our reconstructing the plate tectonics around here. Now there are other plates, like the Pacific plate, that when they come down and hit the transition zone, which is a big viscosity contrast, lower mantle has much higher viscosity, it starts to buckle and thicken enormously. This is a numerical model somebody did showing this kind of slab buckling. And so this goes down to around 1,100 kilometers, but it ends up being very thick. So we can map out the edges of that slab with some error associated with that, and then we can unfold it, assuming that it's originally about 100 kilometers, which is roughly the thickness of oceanic plates, and we decompress it and so forth, and we might make different choices of how thick that would be, and so we have some original length that would be like 3,700 kilometers plus or minus. I don't know, 500 kilometers or something like that, or 300 kilometers. And also we know it's still attached to the Pacific, so we know the motion of the Pacific plate during this time. And so we can say that subduction began around 50 million years, plus or minus 50 million years. It's fairly large uncertainty just because tomography isn't very high resolution, but even this is a huge advance over no understanding whatsoever. So we can accommodate that pretty well. And so it's about roughly 50 million years and about 3,800 kilometers subducted. Okay, now let me, so this was just right here in the Marianas, and if we go northwards and look at various slices, it actually comes down and flattens out, like I showed you before, closer to Taiwan. The Pacific plate flattens out, so it's quite different shape. Here's actually a little model of that. This is a mid-slab slice with all the earthquakes. The Marianas are down here. This is Taiwan, Japan, and Korea. We have this flat Pacific plate under Dongbei, basically. And let's see if I can, yeah, this is a movie. And we can see we have an abrupt change between a very steep plate and the flatter plate. It's progressively tearing, apparently, as it subducts. And so this is the Pacific plate, and the Marianas subducting very steeply, and then the very flat subduction that comes actually very close to Taiwan. Just north of Taiwan is this boundary there. And these are the seismic velocities within them. Okay, so so this is up near Tokyo section, and we can do the same thing. We can measure the area of this slab, and we get, in this case, about 4,900 kilometers of original plate, but it's about 50 million years is the beginning of subduction. So that's interesting. We get the same answer. And it turns out that if we do this for different slices, we end up with these different pieces of noodles, basically. We unfold. And if we move back the Pacific plate at 50 million years, it pretty much fits against Asia there. So that would be the beginning of subduction of the Pacific plate in these different sections. And so we can roughly reconstruct the Pacific plate. And so this would be a plate reorganization event at this time. So this would be like fitting together Africa and South America at this time. And then if we take our Mariana sections, they're not as long. It's only 3,800 kilometers. And so we actually have to have the edge of the plate where it starts subducting is out in the ocean. It's not along the edge of Asia. And of course, that's where it is today. The subduction system goes from Tokyo southwards towards the Izu-Bonin and Marianas. And this actually keeps on going and all the way down to New Zealand. New Zealand is right here. And so we can, this is the bottom of all these slabs at about 50 million years ago. And so this would be where the beginning of subduction would be. That's our prediction. And then we have a huge area here. Look at this huge area of no plate. There has to be some other ocean there. And so where's that plate? It's all been completely lost. It's an ocean that was between the Pacific Ocean and the Indian Ocean there. And it also includes what's called the Proto-South China Sea as well. Okay. Oh, now first of all, if we look down at the level of the bottom of those slabs, that is around 1,000 kilometers down, we actually see that going from New Zealand all the way to close to Japan, we actually see that in various tomographies, though the equatorial region doesn't always show this in all the tomographies. And so that seems to be the edge of this Pacific plate in the tomography. And so we think there must be some plate reorganization event, some change in motion. And this is actually at about the same time as the Hawaiian Emperor Band. And it had already been proposed many years ago as the beginning of subduction in Western Pacific that starts to draw the Pacific plate towards the west. Okay, so we have all these unfolded slabs, but we need to find something in here. And so we'll look at a seismic section from Tonga up towards Japan. It's this section right here. And so this is south, Kermadec Trench, and then this is the Ryukyus would be over here. And much of the way along here, you have a flat slab in the upper part of the lower mantle. It's not a single slab, and it's not a constant depth. There's also a Manus plume here that's, I'll point out a little bit later, that shows up in this tomography. And then here's a couple of other east-west slices. We see this flat slab, and these are all broadly called the East Asian Sea. Johnny Wu decided to call this East Asian Sea, and so when you map this out, you fill up pretty much all this space, but there's some holes in it, a few holes in this. And what we're going to do is we're just going to move this straight up from where it is. We're not going to try to rotate it or anything like that. Just move it straight up. And it actually fits right along the edge of the Pacific slab there. So right there, and this is the Proto-South China Sea. And it basically fills this space, except for a couple of holes, 2 holes in here. But now these gaps here, these smaller gaps are within the error of the tomography and the mapping of the slabs. But the first order that fills that whole space just by bringing it straight up. And so that also suggests that these slabs just sink straight down in the mantle once they're subducted. And we have, because there are 2 holes, we have several possibilities for what we can put in there. There's still a plate that we didn't put in here. It's the Molucca Sea slab. And the Molucca Sea is very similar to Sunda, and it's right, in fact, it touches it, so it clearly fits in there. And this is the equator right here. So this is where we think that those Mesozoic parts of the Philippine Sea Plate, including the Huatong Basin, fit right in here, is our idea. And though we have another model that sort of somehow squeezes this over here, it turns out it's not so satisfactory. But this one, basically the Huatong Basin would be in here, and then this part of the Philippine Sea Plate, the West Philippine Basin, is sitting right over the Manus Plume. And it turns out there is a plume track on the, in the West Philippine Basin. And so let's see, this is a movie. I want to show you the motion. So we're just going to drive, we're going to have the Philippine Sea Plate increase in size according to its spreading ridges, and we're going to push it with the Pacific, basically. And so here we go. This is the growing Philippine Sea Plate. It's this plume track developed until it moves off the Manus Plume. It's rotating here. Here's the Caroline Plume growing along here. It rotates, and then we get a collision with Southwest Japan, and then in just a second, a collision with Taiwan right there. And so we've worked out to the first order the motions of the Philippine Sea Plate. Though this is really a class of models in many ways, it can be perturbed in various ways. But so that you can see there's a large rotation of the Philippine Sea Plate. The Pacific first was subducting underneath the East Asian Sea, and then that subduction system is actually amalgamated with the Philippine Sea subduction system. Okay, so these the other model is essentially is pushed by the Australian plate. It would just move straight north. So I didn't show you that model, but this is our favorite one. It has this rotational motion. And these 2 different models have different predictions about the geology. And the plate model is really developed with Johnny Yu and I with the minimum of geology in it. We just really are using the known plate tectonics of the larger plates and the slabs. And then we then test it against the geology. And so this is actually a massive paper. I think it's like 80 pages in JGR, plus supplemental materials. It's like a book, but it gives all the techniques and methodology plus the testing. And so here's just one example. Here are 2 boreholes in the Philippine Sea, and they have a long paleomagnetic time series. And so these 2 are both in the plate. So does that line connecting them rotate or not? Well, the 2 different models, the red one actually fits it quite well. The blue one is the Australian motion. The red one is our favorite motion. So paleomagnetism fits pretty well. Oh, here's another aspect of paleomagnetism. So originally, that line would be oriented like this with the new Philippine Sea Plate, and then it's rotated to this new orientation. And it predicts pretty well rotation, or the plate model actually fits the data pretty well there, even though there's a lot of error in the data. Now, there are lots and lots of implications to the tectonics of East Asia from models of this sort. And one of them is that first year, the Philippine Sea Plate is running over the East Asian Sea. So here at 23 million years, we're just about subducted the whole East Asian Sea. And then we're running over that east-west tear in the Pacific Plate that I showed you before. And so it starts to run over the Pacific Plate here. And we have still subduction of the Pacific under the Ryukyus at that time. So we're going to have an arc collision here. And Taiwan eventually will be right here. So we still have South China Sea is actually forming at this time at the edge of the East Asian Sea. And so if we go a little bit later to 16 million years, we're already colliding, and we actually start to get magmatism in the forearc of Shikoku and Kyushu, and we have a prediction of a collisional mountain belt here. And we actually see that in submarine fans that feed out onto the Philippine Sea Plate derived from Asia at that time. And this is a mountain belt that was not really recognized in the literature very well, but you could actually see it in petroleum seismic data. We have a lot of deformation just before and big unconformities in the East Asian Sea there. And then, if you take the present plate motions and just extrapolate them backwards and say, well, that's our model of tectonics of Taiwan, we find out if we just go back 10 million years at the present rate, we wouldn't be able to have any subduction between the Pacific and the Philippine Sea Plate, which is clearly not true. How am I doing for time? I'm fine, okay. But the plate model that we get from the slabs actually predicts this kind of motion. Essentially, all the models will be some variation on a motion like this that is mostly north-south motion with a little bit of westward motion, about 3 centimeters a year westward motion. And then just the last 2 million years, you speed up to this 9 centimeters a year. And that would be a speed up all along the edge of the Philippine Sea Plate. But in Taiwan, I'll be able to say a little bit about how that motion, that speed up is taken up. But if you go through and look at all the information about how fast Eurasia is subducting in the last 15 million years all the way up to the present in Taiwan, it's about 3 centimeters a year. And so that we get this kind of, we could start to think about, that we have this subducted slab, but we could start to think, what is the Philippine Sea Plate running over? So this is the track of the coastal range. And the coastal range is actually going to run through the old ridge here around just after it stops spreading. And the East Taiwan ophiolite actually has geochemistry that is very similar to volcanic rocks near the ridge here. So it's very likely that ophiolite was collected as it ran over about 10 million years ago, and then it's going to run over, and then eventually it also, there's some stretched continental lithosphere in here that is going to run over, particularly farther south in the Hunchuan Peninsula. We have the Shimen conglomerate that you see when you go on the field trips there. That's in Upper Miocene there, and so that's an orogenic event that's associated with running over this material. Maybe 7 or 8 million years ago. So this is one, I'm getting near the end of this, and this is a map of plate convergence relative to Eurasia. So there are certain gradients in it, 3 different places where you have a lot of deformation that's taken up. One is in the western foothill thrust belt, that's about 3 centimeters a year. Then in the longitudinal valley, and then under the coastal range and offshore, those combine to about 6 centimeters a year. So it's interesting that only one of these, only 3 centimeters a year, is actually involving materials of the Eurasian plate. The rest is actually deformation of the Philippine sea plate. And we see that deformation just in the bathymetry. Here's the arc coming up and becomes deformed in the coastal range. And then the western limit of Philippine Sea lithosphere from OBS surveys, geophysical surveys, comes up here. And we see the Forearc Basin going from 110 kilometers wide to essentially 11 kilometers or nothing practically in the coastal range where all the beds are vertical there. And so we've lost about 100 kilometers of lithosphere. We also have some thrusting offshore. I don't think I put in any picture of that, but that takes up another about 30 kilometers of shortening there. So this, that's enough to account for this speed up of the Philippine sea plate by 6 centimeters a year for about 2 million years ago there. And so this is what's lost. And we see that right in here. I thought I had a, yeah, here's a map. This actually first showed up in Uymin's tomography. So this is the slice at 35 kilometers depth. This is the shear wave velocity. This is the lower crust of Eurasia with the moho coming along here. And then this is Philippine sea plate. And then between the Eurasian subduction zone and the Philippine sea plate is another secondary subduction zone, and there's a very thin zone of mantle and crustal velocities. It's very continuous and actually continues at deeper levels farther to the north. And that's the subducting front of the Philippine sea plate. So, and we also see that in P wave velocity as well. So, so this plate reorganization is actually taken up by this deformation of the edge of the plate, and it's the main Eurasian subduction has not changed at all during this period. Now, other places around the Philippine sea plate, there have to be other mechanisms for taking up this speed up of the motion, but this is how it's happened with Taiwan, and it's only transient. It can only, it's almost done. It's essentially completely subducted in northern Taiwan today, and so that the motion has to be taken up some other way. And here it's taken up by the change in polarity of the subduction. So this can, and also the opening of the Okinawa Trough Back-Arc Basin there. Okay, and so this is, I didn't have time to show you tomography under the Chingshui Cliffs here, but it's actually quite a wild structure underneath here. I guess I'm out of time, unless you want to know about what the Mesozoic, but we actually have deeper slabs that we're working on. I can show you just in about 3 or 4 or 5 minutes of that. But, you know, in the Mesozoic, this is 80 million years ago. This is Upper Cretaceous. That's everything that's lost. And so, but we know, and this is roughly where the Philippine sea plate would be someplace, you don't know where, but at this time we know that, or earlier in the Cretaceous and the Jurassic, we knew that we have subduction along here. There's a lot of tectonics on this margin. And so what about this Mesozoic history? It's going to be deeper. It's going to be represented, the subduction is going to be deeper. So this is a graph actually of age of subduction of lithosphere versus depth. And so we need to be looking at like 1,500, 2,000, maybe even 2,500 kilometers for this tectonics. And here's some of that magmatism going from Vietnam, South China, Korea. Japan is not actually compiled in this map. And in the early Cretaceous, it goes through here in Fujian and so forth. And, but then in the south, it largely turns off in the late Cretaceous, but continues on to the north there. And so there's also a lot of other metamorphism, deformation, basin development that's at this time. And there are many different plate models of this. And so it's sort of like the Philippine Sea Plate. You had many different models of the Philippine Sea Plate because you weren't really constrained. I mean, you were constrained by the geology of the edges of the plates, but that is not strong enough constraint to really give you a unique solution. And so we've started to do some work on this, and there's actually a bunch of different slabs in this region, and I'll just show you a few of them. This is kind of, unfortunately there's no geography on this diagram, but we're looking towards the north. This is the flat Pacific slab that I've shown you before several different times. And then this would be the beginning of subduction of the Pacific 50 million years ago. And then there's a gap in plates, and then you go to the Izanagi plate. That's what was subducting before. So that's the ridge subduction of the Izanagi plate. But as you come south, you come to a different plate that we're calling the Hunan slab here, and the top of that is deeper. It's 1,400 kilometers, so it ended subducting quite a bit earlier. And then there's a slab that actually comes right under Taipei that we're calling, my postdoc, Ido Liu, is working on this. He decided to call this the Taipei slab. And I'll show you a little bit about these, not very much, but just to indicate that there is some deeper structure here. So that you can see that we're looking head on at the Izanagi slab, and its top is around 1,000, and 1,400 kilometers for the Hunan slab. And the Izanagi slab has a bottom here. Hunan slab goes down essentially to the core mantle boundary there, though it might be sitting on other slabs. It may not be continuous there. And the Taipei slab we're sort of looking at end on here. Now here's a cross-section through the Taipei slab. This is going from, say, the Sea of Japan, very close to Taiwan, through the Philippines, to Borneo. And this is the flat Pacific slab. This is the Proto-South China Sea slab. And then this is the Taipei slab going down, and it may continue all the way to the core mantle boundary. It's not real clear about that, but at least in this tomography slice, it looks like it may. So there's some, this is to say that there's a lot more history under East Asia, so I think we can go much farther with the plate tectonics and understanding the history of this very complicated part of the world. This is another kind of crazy map, but this is a map here. So Japan's here, this is the Bohai Bay and South China, this is Hainan, it's right here, Philippines. And so Taiwan's here, and this is the top of the Taipei slab. There's kind of a big low velocity zone in it. This may be actually a gap between different slabs, and then the deeper parts of that. The section I was showing you before was through here where it's more continuous there. And yeah, let me just skip that one. But this is just a map I want to show you. This is Korea, Japan, Taiwan's right here, Hainan. And then this is the Izanagi slab and the Hunan slab, and so it would be subducting roughly along here. This does not mean that Asia is in exactly this position at that time. This is present geography. And then this is the top of the Taipei slab at 1,800 kilometers depth. And so this would be essentially, could be a continuous subduction system, but this one is along the edge of the continent probably, because we do have the magmatic belt along here, so it probably is along the edge of Asia. And but this is running straight out into the Pacific Ocean there. And now it's interesting, the Taipei slab is the trench is rotating. So when you get to 1,500 kilometers depth, it's rotating around, it's probably going to collide with Asia. It's going to be some more oceanic terrain that will come in. And we already have evidence of things like that in the geology of Taiwan and other places in East Asia. Yeah. There's other slabs over here. This is Neotethys slabs. These are important for the Himalayas and things like that. There are a lot of different slabs in this part of the world. And then finally, you get 1,300 kilometers, and the Hunan slab is no longer there. It stopped subducting, but the Taipei slab is still subducting, and the Izanagi slab is subducting. There's a Yunnan slab as well there. So, and this is the beginning of the subduction of the Sunda slab there. So this is just to indicate that there's a lot more history down there. We haven't got, we were actually working a number of different parts of the world. Johnny, who has a big group at University of Houston working on these things. We just have a paper, Chenny Wei just had a paper, I think it's about to come out in science, Nature Geoscience, on the Andean subduction. He's done a very nice piece of work there. And so, but we're working all over the world on these kinds of things. And so, I guess I should stop now. Thank you so much.
Thanks, John. John's talk always inspired me. Yeah. Any comment or questions? Okay, John, I have you say the across the Taiwan, the 4 arc is almost close to the Central Range, but you have a Philippine plate is, but from the sub-study from myself and the groups, we are thinking about the 4 arc is just beneath the Philippine sea plate.
Well, it does dip to the east at a fairly steep angle, about maybe 70 degrees. Yeah, so it goes back in under the Philippine sea plate, but and you can actually trace it. But it can be, in some parts they're very steep. When you're at Lu Dao, you actually see it in the seismicity there. But it's not flat or anything like that.
I think that this should be the 4 arcs beneath the subduct, beneath the 4 arc, beneath the Philippine sea plate.
I didn't put in any slides. Well, let's see. Maybe one of these I have. Let's see. Yeah, I didn't. I figured I didn't have time to show that today. Yeah. Well, here actually, this part is. This is closer to the. Let's see. This is. Okay, so this is an area where it is maybe more like what you're saying. This is actually just a little bit south of Taiwan, and so the 4 arc is in here. The 4 arc and perhaps arc lithosphere. This is the mantle lithosphere of the Philippine sea plate, and so this is dipping. This is actually as you go north, this becomes much steeper.
Yeah.
There, but just right around Taidong, it flattens out very pronounced there. That's certainly true there. Yeah.
Just in the north one, and almost overlap beneath the Philippine sea plate. Okay.
Oh, near Hualien?
I guess this is why they cross Taiwan. They have the double seismic zone due to the 4 arc plate beneath the Philippine sea.
Yeah.
So the area have the double seismic line. Based on our
we need to talk about that. I'll actually be talking about some of that at AGU.
Okay.
That's a very complicated 3-dimensional system there. But the there's a huge subduction channel there. I don't know if you've probably seen this huge. It's about 35 kilometers thick, and it goes down to about 70 kilometers. You have all this sediment subducting there, and it may even go quite a bit deeper than that. So this is certainly getting metamorphosis and so forth. But there's a roof thrust to that, and a floor thrust, and those those are both active, so they may be what's being mapped as a double seismic zone. There, I think so. Yeah.
Okay.
Yeah.
Any Lloyd, you for.
I have a question about the Taiwan fault belt.
Yes.
You said that's the dead previous mountain range. What size should we imagine these mountains? Were they the similar size to the modern Taiwan mountain belt, or smaller? Or?
I presume they could be the same size. I don't know. Not too much is known about them. It's mainly Chinese Petroleum Company shot some seismic and actually drilled a few wells out there, and then the thrust faults are later cut by normal faults of the Okinawa Trough. But there's something called Taiwan Seasea Fold Belt that goes all the way up to Japan, but it's just this western part that is this fold and thrust belt. And it just goes the distance of the original edge of the South China Sea. So it's about 450 kilometers to the east is how far it goes. There, yeah.
Any other question or comments? Okay. In case no, before the close the lecture, I think that today is John's birthday, so we prepare the cake.
A cake?
Yeah.
Wow.
Happy birthday!
Wow. Thank you. Wow, what a surprise. Actually, the last 3 years I've been in Taipei for my birthday, and I've been surprised every time with a surprise party. There.
Candles?
I can blow it up.
Okay.
Yeah, thank you so much.
Okay.
Yeah.
Thanks everyone joined this lecture. Also, we have dessert? No? Yeah, we prepared dessert. You can enjoy dessert outside and continue discuss with John. Okay, thanks.
Okay, great. Thank you.